By the end of section 3 in chapter 8, you will be able to use properties of quadrilaterals to recognize that they are parallelograms. You're going to have a bunch of theorems coming your way, and I advise you not to memorize the number of the theorem because I could care less, but rather the concept of the theorem. So yeah, there's a lot of wordage here. It's a formal way of representing the theorem, and you have it written down on your notes packet, so I'm not even going to read through it. Basically what this theorem says is you want to use different properties of quadrilaterals. So here we have a quadrilateral, and we want to use these properties to prove that it is a parallelogram. And what we have going on here is that DC is congruent to BA, so you have opposite sides congruent, and DA is congruent to CB. Again, opposite sides congruent. Whenever you have those opposite sides that are congruent, we can say that this is indeed a parallelogram. This next theorem relates opposite congruent angles. So the first thing we notice is that angle D and angle B are opposite and they are congruent as marked by those congruency markings. Also angle A and angle C are congruent and opposite. Whenever you have that situation, you can say that we indeed do have a parallelogram. The next method for proving that we have that a quadrilateral is a parallelogram is opposite sides that are congruent as well as parallel. Whenever you have that situation, you have that this is a parallelogram. This last one describes bisectors of the quadrilateral. So if we go and we take the diagonals of this quadrilateral, so DB is one of the diagonals and AC is the second one, these intersect. I don't want you to confuse the term intersect with bisect. Yes, these intersect, but what's important about them bisecting is bisectors cut segments into two equal pieces or two congruent pieces. So since AC bisects DB, meaning it splits it up into two congruent pieces, and DB bisects AC, meaning it splits it up into two congruent pieces, we have that this is a parallelogram. Okay, so in summary, we have the four methods that I just showed you, as well as this first method that I didn't cover in this lesson, but this is just by definition, that if you have pairs of parallel sides, well then it is a parallelogram. So, duh, that quadrilateral is a parallelogram. These other four, the ones we went over, just be able to recognize them, find them, notice them, and use them. So you're going to want to keep this in general in your back pocket to reference back on. You may have seen a ride like this, say if you went to Cedar Point or some kind of amusement park in the past, where you're on these carts and these are all fixed sides and they're actually swirling around in a circular motion. Now, the thing to remember about this is that these are fixed lengths. So we have that this is always going to be 38 and 38, 16 and 16. So when asked to explain why the moving platform, AB, is always parallel to the ground. So the ground would be down here. What it really comes down to is, well, let's prove that AB is parallel to DC. Because they already tell us that DC is parallel to the ground, given by these parallel markings. So really what we have to prove first is that this is a parallelogram. Well, what we notice is equal or congruent opposite sides. So using a theorem that we just learned, again, I don't care about the number, we can say that this quadrilateral, A, B, C, D, is in fact a parallelogram. Which tells us that, well, by definition, all parallelograms have parallel opposite sides. So side AB must be parallel to side DC, which must be parallel to the ground. Here's the solution to the last question written out. You can pause it now and write this down if you'd like, but I'm just going to move on. Here's a picture of a doorway that has been leaning over time. And the question here is to explain how we know that SV is equal to TU. Well, what we're given is opposite, congruent, and parallel sides of a quadrilateral. So because of that, we can use one of the numbered theorems. Again, number, who cares? I don't. Just know how to recognize these properties. So the properties that you recognize first are, well, what I just mentioned, opposite, congruent, and parallel sides, which tells me that this is a parallelogram. So quadrilateral STUV is indeed a parallelogram. Now that we know that it's a parallelogram, we have a theorem earlier on in the chapter that told us that all opposite sides of parallelograms were congruent. So we could finally state that SV is congruent to TU. And we're done. So the basic process here was first recognizing that our quadrilateral was a parallelogram, and then using anything we know about parallelograms to prove what we were trying to show. Again, here's the formal solution written out. You can pause it if you'd like and copy it down. I'm going to skip ahead to the next question. Now we will apply some algebra to the different properties that we've learned about the parallelograms. So here we want to find a value for x that would actually make this into a parallelogram. What I notice is that we're given diagonals, and we have that FD bisects CE as shown here with these congruent markings. In order for this to be a parallelogram, we must also have congruency on FD. So FN must be congruent to ND. Therefore, CE would be the bisector of that segment. Since those must be congruent, we can simply just set up the algebraic expression that Fn is equal to ND. Now to solve, so I had that Fn was equal to Nd or Dn, whichever way you want to put it. From there I can substitute. We have 5x minus 8 is equal to 3x. I'm just substituting in the values they gave me. And now solving. First thing I can do is subtract both sides by 3x. So I subtract 3x from this side and this side. I get 2x minus 8 is equal to 0. Add 8 to both sides. 2x is equal to 8, which means divide both sides by 2, x is equal to 4. Now I'm not done yet. Okay, I found x is equal to 4, that's great. Let me check my answer to make sure. So we can plug back into Fn, 5 times x, which now is 4, minus 8 gives us 12. Plug it back into Dn, again we get 12. 12 equals 12, so we did something right. Our final answer is yes, this is a parallelogram when x is equal to 4. Last question of this section, we're going to look at a formal two-column proof. Don't freak out. This isn't as difficult as you may think it might be. I know that proofs seem like this crazy concept, but I'm going to walk you through it step by step to help you out a bit. So step 1, we have to always state our givens. This is the easy part. Why? Because the given was given, so just put it there. We also have what we need to prove. ABCD is a parallelogram. Let's write that down into step 4. Alright, so we just got 2 points out of, it looks like 5 in this question. Let's start filling in the rest of the problem. So after we state the given, the next step is that AB is congruent to DC. And we also have that angle BAC happens to be congruent to DCA. So I'm going to mark those down in my picture. Now we have to think back to other chapters, previous lessons, as to why we could say this fact. Well, we're given that two triangles are congruent, which means that every piece of those triangles are congruent by CPCTC. Remember that one? Corresponding parts of congruent triangles are congruent. So just remember how I figured this out though. Given the way that this was written, ABC, that's triangle ABC, was congruent to triangle CDA. That means that AB and CD are congruent if we're looking at the segments, and that's exactly what we just used. We could have also said that BC and DA, those segments were congruent. We could say any of the angles were congruent. So CPCTC is a good tool to use. Step 3, blank. What do? Well, we've already got opposite congruent sides, so if we want to prove a parallelogram, we have to take something out of one of those theorems that we learned today. And we could either use opposite sides are parallel, or maybe prove another congruent side. There's many different ways to approach this problem. In step 3, they've already got filled out. The reason, if alternate interior angles are congruent, lines are parallel. So we have that these two angles are alternate interior angles. So the lines that are parallel would be line AB and DC. So in step 3, I write AB parallel to DC. Last step, why can we now say this is a parallelogram? Well, if we look up to our picture, we've shown that these are parallel and congruent. So the opposite sides of this quadrilateral are parallel and congruent, which means by theorem 8 point blah blah blah, who cares, we could say that since we have opposite sides congruent and parallel, i.e. this is a parallelogram. Don't write the number of the theorem down. I really could care less. Know what you're talking about. Just explain yourself, and that's it. Alright, so now it's your turn to practice, and we'll be doing a lot of these in class, so be prepared just to recognize different properties of quadrilaterals to state that it's a parallelogram.